Okay, let's get started today. We're going to talk about soil test trends. We're going to take a look at the TFI soil test inventory and some other data around soil test trends and what those mean for nutrient management. Just a note before we get started on the CCA continuing education units. We're still waiting on approval for this. We had a little delay in getting the approval. So we're still waiting for that approval. So there are two options for you to get your credits. At the end of the presentation, we can let you submit your name and your certification number into the Q&A, and then we'll take those and submit those once we get approval. But also everyone will receive an email when the recording is ready, is all prepared. And you can watch that recording and there'll be a short quiz at the end of the recording. You can take that. With that, we're going to get started today. But before we talk about the soil test trends and some of that data, we want to talk a little bit about soil testing and what it is and what we're going to be looking at. Soil testing is a key part of this 4R nutrient stewardship that we promote, using the right source, right rate, right time, right place. Soil testing is an integral piece of information in making those decisions. So it's important to consider that piece of information in the context of everything else that's happening. Now, let's understand what the soil test information is. I describe the soil test as a probability indicator. So what do I mean by that? It indicates the probability of getting a response to added fertilizer. And you might also look at it as an approximation of the potential nutrient supplying ability of the soil. Now, we're not measuring in most cases the exact nutrients that the plant takes up, but we're measuring some amount that relates to what the plant takes up. So it's an indicator, and we're using that soil test as an indicator of whether or not we should apply more fertilizer and how much. So I like to use this graphic, pretty simple concept. It's at very low soil tests, we have a high probability of getting a response, and we usually expect those responses to added fertilizer to be larger. It doesn't mean we'll always get a response because there may be other limiting factors. For example, if my soil test phosphorus is low, but I don't have moisture to grow the crop, it may not matter if I apply more phosphorus. Putting more phosphorus on and I don't have moisture to grow a crop, well, I'm not likely to get that response. On the other end, if the soil test is very high, we have a less likelihood, a lower probability of getting a response to fertilizer, and we would expect those responses to be smaller, but it doesn't mean we can't get a response. I've experienced that in some of my own work over my career, where I've seen responses to applied nutrients, say a starter or a specific placement, where the soil test indicated a low probability of getting that response. So it's a probability indicator, but it's one of a number of probability indicators. So we need to take the soil test information in context of all the other information that we have about a field, and it needs to be applied site specifically. So that's going to be a key point we'll emphasize. Now, I like this quote from Dr. Willard Lindsay from many years ago. At the time, there were many soil tests being established and people were studying all the different methodologies. And I think he kind of put this in context in stating that advances in soil testing are not necessarily going to come from finding this ideal extractant for everything, all soils, all nutrients, everywhere. But they may be made by carefully standardizing that procedure and, most importantly, improving the interpretation of that test with the inclusion of all those other important soil factors that can affect nutrient availability. So I really like that statement. Now, along with that, what he's saying is that oversimplification increases economic and environmental risk. That's something I add to that. If we tend to oversimplify, we may miss some of the fine tuning of that nutrient application. It just looking at the soil test report, it says on there, I need so many pounds of nutrients, so I go do that. Well, you may misinterpret some of the other probability indicators that are at work in the field. So let's in any case focus on the interpretation of those soil tests with good agronomics and an understanding of the soil and the cropping system we're working in. All right. Recently, I ran across this paper, and I thought it was quite interesting, and particularly in regard to the topic for today. It was a study published in late last year in a Journal of Agricultural and Food Chemistry. The title is Rise in Potassium Deficiency in the U.S. Population Linked to Agricultural Practices and Dietary Potassium Deficits. So there were a number of interesting findings, and the research group here took a look at all kinds of fruits and vegetables, and they surveyed some medical data on human nutrition. And so there's lots of sources for this information listed in the paper. For those who are interested, you can look it up. I've given you the reference there. But some of the key findings. Overall potassium intake in U.S. adults is declining and has been declining for some time. A potassium deficiency called hypokalemia is increasing in frequency. So the observations of the authors in the paper was that hypokalemia, based on blood serum potassium levels, has been on the rise. So along with that, the potassium concentrations in a number of major food groups, most notably beef, pork, turkey, fruit, vegetables, some of the cereal crops, and others, have decreased from 1999 to 2015. So they're tying all of these things together. And they also noted that long-term potassium removal from soils exceeding potassium additions to those soils has led to this food potassium decline. So what they were able to do is link soil test levels for potassium to human nutrition and the potassium in our food. So the last bullet there is a quote from the authors. They hypothesized that continuously rising high ratios of crop removal to input. So in other words, higher yields, removing more potassium in relation to the input in US farms are unsustainable and have contributed to worsening K intake in the US population. So it was a very interesting paper, particularly in regard to our topic today. So we're going to talk about some of these soil test trends and what they might mean for us. Here's a couple of graphs from that study. Here is the serum potassium levels in US adults. So you can see from 1999 to 2015-16, it has declined, although it appears to have stabilized over the last decade or so, somewhat. And then here they've plotted the potassium input to removal ratio. So in other words, a 1-to-1 ratio means that for every pound of potassium that was removed, a pound of potassium was applied. So in this case, we have ratios less than 1, meaning that there's greater removal or less input per unit of removal. And that has declined steadily over the last several decades. So that's just part of the information taken from the paper. All right, so let's talk about this soil test inventory. It was formerly conducted by the International Plant Nutrition Institute. With the closure of that institute, that has been assumed by the Fertilizer Institute. It's taken responsibility for that inventory. And so we want to take a look at that and what that is. This is the website that you can go to, and you can find all kinds of information. You can chart that information. You can create maps. You can actually download the actual data and use that. We're going to show you a small sampling of some of the things that are there and some of the interesting findings in that inventory. Now, I will also note that there is a new inventory from 2020 that should be out sometime this year. It's still in the final review stages, so the 2020 inventory is not yet available, but should be before the end of the year. So we'll look forward to that to see if some of these trends continue. So what does this inventory consist of? So the Institute solicited soil sample analyses from commercial and public laboratories across North America. In 2015, it was composed of over 7.5 million samples that were submitted. So they contact the labs submit their data, their analytical data from all the samples they received. It's completely anonymous, so there's no concern about confidentiality. They simply submit the numbers. Those samples are scrutinized through and through for possible errors, and there are some potential error sources in such a survey. The data are then standardized, they're consolidated, then analyzed statistically, and then through the website you can classify the test ranges are classified, they're plotted, they can be mapped. And so you can gather some information from this soil test data. Now, we need to consider the potential limitations. Keep in mind that these are high-level state and provincial trends. These are not site-specific soil test values. So they're data compiled over many, many samples. And some states have several 100,000 samples that are part of this inventory. Other states only have very small numbers of samples, so the data may be less reliable. Now, I said here that the data does not reflect soils not sampled. Well, that's kind of obvious, right? My morning profundity, as it were. What this really means is this is a potential limitation in the data and a potential source of error, in that we may suppose that the better managers are those that are soil sampling, those that are taking these samples regularly and using that information probably reflect better managers. Those who are not sampling, we don't know what their soil conditions may be, what their nutrient levels may be. And in some cases, we may be missing some soils in this inventory that are of concern, either very high levels or deficient levels that should be noted. So we don't know what isn't sampled there. And as I noted, there are some states and provinces where there are very small numbers of samples submitted. In some cases, laboratories, private consultants choose not to participate. So we may have large gaps in some of that data. In some states, there simply aren't enough data points to provide any information. There's also some uncertainty in calibration equivalency. Now, why is this important? Well, particularly with phosphorus, but this is true for all the nutrients, there are multiple analytical methods for deriving these soil test values. And for example, with phosphorus, we have the Olsen test, we have the Bray test, we have the Blaylock test, and we have a couple of different Bray tests, and there are other methods that are used. So to put them in some kind of equivalency, they have to evaluate those and try to convert them all to some kind of standard equivalent measure. So that is certainly a potential source of error because they're not exactly comparable. An Olsen test can't exactly be converted to a Bray test, but we have to come to some kind of equivalency in order to do this inventory. So there is some uncertainty in that calibration. There's also uncertainty of manure effects because manure may be applied one year and apply a large amount of nutrients to a field, but not in another year. And so the labs, most of the labs in the inventory did not identify whether the fields were manured or not. So there's some uncertainty in those effects and some of the changes that we see. So that's the data we're going to be looking at. Recognize that there are some limitations. Most importantly, recognize that these are high-level trends and not site-specific evaluations of soil test levels. So they give us some indications of what is happening in the world of nutrient management, but they don't give us specific recommendations. So please don't interpret it to mean that. Now, we have our Nutrien eKonomics website, and we also have the same information available. It's formatted a little bit differently and displayed a little bit differently. You can go to the website and you can select any state or province and pull up the data for that state or province. And we're using that soil test inventory database as the data behind this interface. So it's the same information, but just presented in a little bit different manner. I'll show you an example from that a bit later. So that's the data that we're going to delve into. So let's take a peek at that. So one of the things you can pull up is a map of the percentage of soil test samples that were submitted that are below the critical level established for that nutrient in each of those states or province. So for example, we look at the Great Plains states and the Canadian prairies, we see a high percentage of the soil samples that are deficient in phosphorus. They're below the critical level for those states and provinces. So we know those soils, we've long known those soils are naturally low in phosphorus. So that's not surprising. What it does tell us is that we need to be very attentive to phosphorus management in these soils because we're largely growing wheat in many of these areas. Wheat is very responsive to phosphorus. It's very critical for the establishment of yield potential. So that gives us some clues that this is an area in the plains, particularly the northern plains, where we want to pay particular attention to phosphorus soil testing. Then there are some other areas, excuse me, where most of the soils are above the critical level, and maybe it's more of a concern of having excess phosphorus. For example, some of these coastal areas, the Chesapeake Bay region, where phosphorus runoff has been a problem, the Lake Erie Basin. So some of those areas, we want to pay attention to that for other reasons. So but we see on the map, there are a significant number of these soils that are below optimum. So that should be a factor in our nutrient management. And I should stop here and remind you that if you have questions, please submit them to the Q&A box. There's an indicator at the bottom of your screen for Q&A. You can open that, type in your questions, and I'll see those as they pop up. Some of them we may be able to take during the presentation. Others we'll answer at the end. So this next map is just a map of the critical levels established, the Bray P1 equivalent soil test critical levels established by the different states. It's kind of interesting to see how there's quite a bit of variation in the critical levels that those states are using. Now, the states and provinces come to this through research and correlating crop response to given soil test levels, adding fertilizer, evaluating the response, and calibrating that. So that's a process by which these critical levels are determined, but we see a fair bit of variation across the country. And the question has long been asked, well, why should they be different simply because we cross a state line? Why should the critical level be 20 in Illinois and 15 in Indiana? So there's a research group that's currently working on some of those issues and trying to see if they can come to some kind of standardization. But so with this as a backdrop, now let's look at the change in the median soil test levels. So we looked at the number of samples that are below that critical level. Now let's look at the change in the median. So if we look across the country, we see, again, in the plain states where phosphorus is a concern, the median soil test level is increasing slightly. Some of these soils are calcareous soils. They have high phosphorus fixing capacity. It can be difficult to raise the soil test in those states. And it's particularly hard to justify adding large buildup applications in dryland wheat where rainfall is uncertain. So there's a reason why we don't see a larger buildup there. In the east, we see the median soil test values actually declining somewhat. And so in many areas, it's not changing a lot, but there are some areas where some things jump out at us. And I look at Florida particularly. Now, it's not surprising that a lot of soils in Florida would be high in phosphorus. That's where a lot of our phosphorus mines are. And so okay, that's not surprising, but we see a big jump, an increase in the median soil test value by 55 parts per million. And that would be of concern where there are such large concerns about phosphorus runoff from the various municipalities. They're close to the ocean, and eutrophication of those waters. So we have a question that's come in. are the differences between Bray P1 critical levels based on variance of crop responses, the inherent pH, or both? Okay, that's a great question. pH certainly influences phosphorus availability. However, in the process of calibration, correlation and calibration and determining of those critical levels, that is it's kind of a black box approach. We plant the crop in soils of different phosphorus levels, and we measure the response, and we add fertilizer and determine the point at which no further response to fertilizer is observed. So that pH is kind of built into that critical level in the process of that calibration. Hope that answers the question, but it's maybe an oversimplification. Now, I know there are some places, particularly in Idaho, they make adjustments in the phosphorus recommendation for soil lime content, for calcium carbonate in the soil. There's lots of soils with high free lime, which increases the phosphorus fixing capacity. So in that particular state, they make an adjustment for that. It's not strictly based on pH, but based on the higher P-fixing capacity in those high lime soils. All right, so another area that I noted on the map here in the Chesapeake Bay region, some pretty large decreases in the median soil test P level. There's been a lot of effort devoted to improve nutrient management in those areas and stopping runoff of nutrients into the bay. So that could be reflected in that. Although when you look at the individual states, the values in Maryland show also a significant number that are still below the critical levels. So, but there has been an effort to better manage nutrients, P and K, and avoid those really high testing soils. So that could be a reason there. But again, you have to look at the local management, the local processes, and the specifics to that region. So only take these as high level indicators. And one jumped out at me up here in New Brunswick at 85, an increase of 85 in the median soil test level. And I went back and looked, and I couldn't find any particular drivers that jumped out at me for that. It's a relatively small number of samples, so it might be one of those cases that's more prone to error, that we want to look more in detail at local management before we react too strongly to that. So there's a comment here, data on P and K status in soils are shown for a period 2010 to 2015, relatively old data. How about a new set of data? Yes, these are relatively old data. 2015 was the most recent survey. As I indicated, the 2020 inventory will be out sometime this year, and we certainly want to go back and look at these trends with the most recent data when that's made available. But it is coming. It's coming soon. It's under the final review. I've been able to get some of that data for personal use from Tom Brulsema, who's kind of the steward of that project. So the data is there, but it's not yet available for public consumption. Okay, so one of the factors in these changes that is interesting to look at is what we call the removal to use ratios. And this is a different program here. This is a system called NUGIS, which is also managed by TFI. And this takes data from commercial fertilizer use and manure application data, and it compares it with crop removal as estimated from crop yields multiplied by a concentration factor. So for example, concentration of phosphorus in corn grain, for example. There's some standard values for that. Obviously, that's a variable number, but using those values and the commercial fertilizer sales data, we can draw some comparisons in removal to use. And so we can look at a map like this and say, okay, why might soil tests be declining in a particular area? And so we look at the Great Plains and we see that removal exceeds usage. So the ratio here is is removal to use. A ratio of 1 means that removal is approximately equal to total nutrient applications. So we can look at that. And we see in this orange area here in the plains, we're still removing more than we're applying in the crop. So Western Corn Belt, the Great Plains, the yellow areas are those areas where it's approximately in balance, which is, as I interpret, a good thing. And then these green areas where the removal is less than the actual applications. Now, these are plotted for the cropland only. You can view the whole map, but some of the data doesn't make sense. For example, out here in the West, we have large areas that are just rangeland or mountains, and so that data doesn't make sense, and you can put the overlay to only show the crop data. So there's another comment that's come in here. I noted the increase in New Brunswick phosphorus soil test levels. So the comment here is there's a lot of potato production. If there was a small data set, potato growers could have been driving the high P values. And yes, that was something that occurred to me. That area is dominated by potato production. So that's a good comment to note. And potatoes are certainly a big phosphorus user. They require a higher phosphorus level than some of our grain crops. So that's an important thing to note. Okay, another comment has come in. So some great discussion, great questions. Nitrogen is one of the 3 major nutrients. There's hardly any information on use of N fertilizers based on soil test values. Also, there is absence of method of N estimation in soils for working soil tests versus fertilizer rate. Great question. And that is something that's somewhat locally specific. In the Western US, soil tests for nitrate are commonly used as part of the nitrogen recommendation. So we look at available nitrate in the soil profile, and we know that's going to be available to the crop. And so we include that in the nitrogen budget. However, as we move into the eastern regions where soil organic matter is higher, rainfall is higher, that nitrate value is so transient that it's not particularly meaningful in terms of making a nitrogen recommendation. Now, a number of people have been working on methodologies to try to estimate various nitrogen mineralization tests, the contribution of that organic nitrogen to that. And so there's ongoing work in that area to fine tune those. It's still kind of problematic because nitrogen changes so rapidly in those systems. There are things like a pre-side dress nitrate test. So let the crop get established, go out at some of the early vegetative growth stages, take a soil test sample before you're going to side dress, see how much nitrate is present, and then adjust your side dress according to that. So there are some of these methodologies, but the problem with nitrogen is the transience of available nitrogen in the system and the predictability of the availability of those organic forms. And so that has long been studied. It's complicated, and that's why we don't have so many nitrogen soil tests or nitrogen tests as an indicator of the amount that needs to be applied. That's based more on correlation with the crop response and evaluating past responses for specific crop rotations and soil types, and there are various formulas used for that. So great question. We do use that soil nitrate in the West quite commonly for a number of crops, but not so much when we move into higher rainfall regions. All right, so crop removal to use can give us some information as to why things are going the way they are. And this comes back to the point that was made in that paper on potassium nutrition. This is the data that they were looking at to evaluate those that removal to use ratio in relation to declining values in the food supply. All right, so I pulled out a couple of specific graphs from the inventory. Here's one particularly. So if we look at the change in the percent of samples from 2001 to 2015. So over that 15-year period of data that we have so far. And we can see some changes here that could be noted as concerns. So now on the high end, a decrease in these very high samples, that's probably a good thing, because these really high soil test levels are where we start to get P runoff, soluble P, in some cases even some leaching. So we want to avoid these excessive levels. But the area of concern is the increase in samples in these lower ranges. So if we take, for example, a critical level of 20 parts per million, we're increasing the number of samples, the distribution of samples that are below that critical level. And so that means we need to pay attention to those levels locally, site specifically, paying attention to what is happening with those soil test levels so that we're not missing yield potential, so that we're balancing phosphorus with the other nutrients. All right, another question has come in here. Should a soil P build program be negated when considering soil pH levels in excess of 7.5? Is there potential to accumulate soil P over time to tie up and consequently low removal? Yeah, so another great question. In these soils where we have high P fixing capacity, it may be very difficult to build the soil test to where we want it, particularly in these high pHs, or in some cases in the very acid soils where P is tied up by iron and aluminum. And it may be difficult to raise those soil test levels sufficiently that, that we're able to do anything meaningful. So in that case, if we're just not able to do that, then we have to take a look at, how do I manage phosphorus in season to optimize its availability? And there are things we can do with placement, timing, and all of those kinds of things. I particularly like band placements. Get it close to the crop root zone and get a high concentration in that root zone to improve that availability. There's lots of attention nowadays on phosphorus solubilizing additives, various biostimulants and organisms that are promoted as solubilizing some of that unavailable P. So there may be some things we can do in season to manage that, even when we can't effectively build soil test P at economic rates. Okay, so anyway, this is a picture of the Corn Belt states and the changes that have been occurring. Just something to pay attention to. The increase in the number of samples in the suboptimal levels would be something of concern. Now, I also pulled out Illinois here just as an example, and I'm not picking on Illinois specifically. It's just showing that same trend. And so I indicate here, so again, a decrease in these number of excessive soil tests, that I interpret as a good thing. So I put a green arrow there, but increasing in the numbers of samples that are below the critical level, the relative frequency there. So, and you can see up here the number of samples that were submitted. In 2010, about 225,000. 2015, over 725,000 samples from Illinois went into the inventory. So that's a pretty large number of samples, and should be pretty solid information. All right, so again, decline in the excessive levels, shift towards lower soil test ranges. We don't want to overreact to those, but it means in our local site-specific management, we should be paying attention to those. All right, now here's one example, again, picking on Illinois, sorry guys, but I just pulled this off of our economics website. This is an example of the kinds of graphs that you can get from our economics site. And here's the nutrient removal and consumption data and the balance calculation of those. So just as an example of the kinds of things you can obtain from our website, if you go there and pick your state, and you can kind of see what, you can get the picture for the general trends that are occurring locally, or not locally, but in your state of interest. All right, so let's move on to potassium. So when we look at the potassium map, again, we look at the Great Plains, notable for their high potassium levels, not many samples below that critical K level as established by those states. But as we go into the Corn Belt, and particularly in the Southeast, we have a high percentage of samples that are below that critical level. Now, These southeastern soils are much more strongly weathered. They're lower organic matter content. So yes, that makes some sense. What we want to look at, then let's jump to the critical levels. So there's still a number of soils below optimum, particularly in the eastern half of the country. So here are the critical levels for each state. And again, we look at the changes across the state lines. And those are kind of interesting to look at and wonder, well, why is it 60 parts per million down in Florida and 80 in California and 170 in Iowa, but yet up here in the Northwest, it's 200. And there's a lot of historical questions to be asked there and about the data and the interpretation and how those were arrived at. And so certainly some valid questions about why they should be so different. But again, recognizing there are different cropping systems, different sensitivity to that potassium level. Again, if I'm farming out here in the plains in eastern Colorado, and I have low rainfall and I'm growing dryland wheat, well, I don't need a lot of potassium. So that may not be of great concern to me. But if I'm growing irrigated corn or I'm growing sugar beets, which are high potassium users, then that's going to be more important to pay attention to. So always interpret these in relation to the local cropping system, certainly the crop response itself, the species I'm growing, and local soil tests. So if we look at the change in potassium soil test levels, the median soil test K levels, we see some decline in the soil tests in the Great Plains, in some states at least. And down here in the South, several states, we see the decline. And there have been some significant changes in some areas. And I look out here in California, a decrease of 41 parts per million in the median soil test level. So, and I wonder, okay, does that matter? I know in California, there are lots of soils at very high soil test K. And the same in Kansas here, where we see a decrease of 66, and in Colorado and Nebraska. Well, I know there's a lot of soils there that are very high in potassium. And so am I really concerned about that? Well, again, I need to look at my specific soil tests, the crop I'm growing, and the response. Again, in Kansas, a lot of wheat being grown. Wheat is not as particularly responsive to K. Yes, it's essential, but it doesn't, its uptake isn't nearly as much. But again, if I'm growing corn or milo, some of those other crops that have high requirements, that decrease may be of greater interest. And so when I look at these, again, I have to interpret all of those in the local context. Now, one interesting point here on the map is Iowa, where we see this rather significant increase in the median soil test K level. Well, some years ago, and I'm not going to give the year because I can't remember exactly, but I'll say 8 to 10 years ago, the soil fertility experts in Iowa took a look at their soil test calibration and decided that it needed to be, that the critical level needed to be increased to reflect a change in the methodology that was being used in switching from wet or moist soil samples to dry soil samples, which kind of changes the value you get from the same soil. So in order to adjust for that, they adjusted the critical level. And so since that time, we have seen a bit of an increase in average, or in that median soil test K level. So that's probably a reflection of a change in the recommendations from the state at that point. So again, we look at removal to use ratios, and we look here throughout the plain states where our soils are naturally quite high in potassium, and perhaps removing more than is being used is not a big deal because we have soils that are 300 or 400 parts per million potassium. I worked in Wyoming for a while, and we had some fields that were 500 or 600 parts per million. So I can go ahead and mine that soil potassium, and I'm not too concerned about having a removal much greater than use when I have this large reservoir, as long as it's available and as long as my crop is able to access that. That's not a problem. So it's justified to mine those high testing soils where they occur. Then here in the Corn Belt, these light yellow areas where we're approximately in balance, that's kind of hard to read. That's about our 1-to-1 ratio. And then the little duller yellow, the little bit darker yellow. There we're starting to move, removal is beginning to exceed the use of potassium fertilizer. So this is again the kind of data that was cited in that potassium paper on human nutrition. And so we can look across the country, and there are quite a few areas where potassium removal is exceeding use and the soil tests are declining. So we can, in the case of this particular paper, they traced that all the way down to the human nutrition component. So that's important to note. And I'm sure some of you have read about the FAO's recommendation to use zinc biofortification. In other words, fertilizing soils with zinc to increase zinc in the food, because zinc is a major nutritional problem worldwide. So I pulled a couple of states that kind of have different patterns occurring in terms of potassium. So here's that Kansas. We see this decrease in those very high soil test levels. Not particularly concerned about that until those soils start to move into these lower ranges where it's not sufficient. But here in Kentucky, we're decreasing across all of these adequate levels and fairly dramatically increasing in the lower test ranges. So there's a point of concern where we want to take a look at local site-specific soil tests and to determine if there's a problem there. Okay, another question popped up. For these studies, a lot of precision is to maintain in soil analysis. This also adds to the cost. While interpreting after analysis, soils are widely grouped into low, medium, and high. There's a question if that much precision is required in soil analysis to start with. That's a great question. I don't know if I have a good answer for that. Historically, we've looked at ranges, low, medium, and high. There's an optimum range. Now with computer technology and our ability to analyze that data to the nth degree, we can get very fine-tuned with the recommendation. But one might wonder if that really is justified. Can we even calibrate our spreaders to, we can make a recommendation to the exact pound with a computer algorithm, but is that really meaningful if I can only calibrate my spreader to plus or minus 20 pounds of a nutrient? So that's a great question. We can, with analytical techniques, achieve great accuracy and precision, but we also have sampling variability in the field. So there are issues on both ends. In my opinion, the chemical analysis is maybe the best part, the most reliable part of all this, because there's so much potential for error in our sampling process. If we're not doing a good job, we don't get enough cores, we're not sufficiently site specific. So yeah, great question. All right. Now, one area I picked out to look at for potassium was the Southeast, because there were a number of states there that were showing some significant decreases in the median soil test K. And when we look at this pattern, so this is for the states listed here across that cotton belt there, we look at this pattern and recognizing this cropping environment is growing lots of corn, soybeans, and cotton, all crops that have high K demand. And as these soils shift from levels that, are in the adequate range to quite a few samples that are suboptimal, that's cause for concern when we're growing these high K demand crops, especially. And again, recognizing these soils are naturally more weathered, naturally somewhat lower in fertility, and in some cases, very low in fertility. Some of the coastal plain sands are very low in natural fertility. So we do need to pay attention to what's happening with these levels. Okay, in the interest of time, I think I'm going to pass that by. Now, one other area that we've noted particular changes in nutrient availability is with sulfur. Now, a lot of people feel that sulfur soil tests are not especially reliable. There's lots of questions about whether or not or how valuable that soil test is in making a recommendation, but nonetheless, it's included in the inventory. It's only divided into 2 levels in the case of sulfur. And we see this change from 2001 to 2015. more low testing samples and fewer high testing samples. And this is a result of a change in atmospheric deposition. So the EPA publishes these deposition maps. So this is from the National Atmospheric Deposition Program, and they report this data on an annual basis. You can go look this up on their website. It's pretty fascinating to watch some of the trends with some of the different things. But in this case, this is sulfur deposition in 1985. Now, about that time, there was something called the Clean Air Act that was implemented. But you see all across the industrial, especially the Northeast, but even down into the South, where we have lots of oil refining. So we see lots of atmospheric sulfur deposition on the order of 20 to 25 kilograms per hectare of sulfur, which often exceeds our crop requirement in some of these areas. So we didn't need to apply a lot of sulfur. And now, as we look at that deposition map in 2018, we see very little sulfur deposition and very few areas that are approaching an amount that would be adequate for crop growth. So we have seen a decrease in the soil tests, and we've seen an increase in the frequency of sulfur response. And now the farmers basically have to pay for what they used to get for free from the atmosphere. So now, not to say that the Clean Air Act is a bad thing, and cleaning up those emissions is a good thing. But it just means we need to pay attention to this nutrient that's no longer being deposited from those sources. Zinc is I think the last one that I'll illustrate here. Magnesium is also in the inventory. Chloride is in the inventory, and you can go to the website and look those up. But if we look across the major grain producing areas of the country, the Great Plains and the Corn Belt, we see a high percentage, to me, what is a high percentage of soils that are below 1 part per million DTPA in zinc. Now, again, understand what that is. In this case, we're not using a specific critical level for comparison as we did with P and K. We're using 1 part per million DTPA zinc as the indicator. Now, for some crops in some areas, 1 part per million zinc is plenty adequate. If we're growing wheat in the plains, 1 part per million is quite sufficient, and we're not likely to get a response at that level. But if I'm growing corn in the Corn Belt, personally, from my experience, I'd like to see that zinc level at 1 to 1.5. And if we're growing some of our crops in the West that have high zinc requirements, sugar beets, dry beans, and some of the vegetables out in California, 1 part per million is likely not sufficient for DTPA. So with zinc, it's very crop specific. It's very locally specific to the cropping environment, the crop itself, the conditions under which the crop is grown, soil pH. I learned this lesson long ago when I was with the University of Wyoming and studying some of the crops out there, that it's quite complicated. There are lots of interactions that we need to look at. But nonetheless, thinking about zinc soil test as a probability indicator, this is a probability that if we're not applying zinc, there's some missing crop response that may be available to the producers for added profitability and better nutrient balance. All right, so we're running out of time. I want to leave some time for any more questions that may come in. pH is also in the inventory, and you can see from this change in pH in the Corn Belt, the soil test trends indicate an acidification of these soil tests from previous levels. So with that, let me wrap up with some summary statements here, and then there's a couple more questions that we'll address. So some of the trends, just by summary, there are a lot of samples that are below optimum in multiple nutrients. So we need to be careful. We need to use our soil test information and manage those nutrients for optimum crop response. And the number of samples that are below optimum is increasing in many areas. So this is more cause for concern. And this was something that was pointed out in that paper on human nutrition. And that's a result of P and K removal exceeding applications in many of these croplands. Now, again, speaking to that mining question, yes, if the soil is testing high, mining may be reasonable, but we should monitor those soils to avoid becoming suboptimal, and particularly suboptimal soils should be monitored and where feasible, either economically or in terms of soil chemistry, to be built up to optimize crop productivity and economic return, should be considered. Okay, so remember, these are general trends. They suggest a gradual decline in soil test levels, and I'll emphasize again, they must be evaluated on a site-specific basis. And maybe not, and maybe even more than just field by field, maybe even areas within a field. And if you look at these on a field basis, you'll see there's a wide distribution of soil test levels across a field. So regular soil testing, keeping good records, watching the trends, considering build and maintenance strategies where it's appropriate. We certainly don't want to be adding more to excessive soil test levels, and particularly examine economics. Now, I say this because for this year, 2021, we have better crop prices than we've had for quite some time. And the value of those nutrients only increases as we increase crop price. Now, yes, nutrient prices are increasing as well, but in terms of the relative value to the crop price, they're still within the ballpark. And so maybe this is the year where cash flow may allow farmers to take some steps to rebuild some of these soils that maybe need some additional application. So examine each case specifically in terms of cash flow and the spreading that cost over a period of time, or getting on a maintenance schedule. And many of our universities have build and maintenance strategies or schedules for those recommendations. So with that, I think I better, I'm going to skip over some of the rest of this, and I think I better go to the end here so that we can address these last couple of questions before we run out of time. So there are a couple more questions that have come in. Is it possible to remove potassium in 2-to-1 clays that it's close to impossible to build K levels back to optimum? Good question. Potassium fixation occurs in these 2-to-1 clays, and the potassium gets into the interclay layers, the clays collapse on them, and then that becomes fixed. Now, in time, those clays do weather, and particularly along the edges of the layers, and that potassium can come back out with clay weathering. Is it possible to build them back up to optimum? In some soils where they have very high fixing capacity, again, like phosphorus, we talked about that. It's kind of the same kind of scenario where it may be difficult to build them to the optimum levels because of the K fixing capacity of the soil. We may be able to do some things with in-season management, and particularly in crops with high demand, looking at like some work's been done in cotton with high in-season demand during the boll filling period with foliar applications, and maybe some other things like that to compensate and get the nutrition we need to the crop. Okay, another question here. Since nutrients can depress uptake of other nutrients, the soil test shows very high P levels, very high zinc levels, but the crop still shows a zinc deficiency. What's the best way to get zinc to the crop early in the season? Okay, great question. And we didn't get into this idea of nutrient competition or antagonism and one nutrient inducing deficiency of another. That's a great discussion for a topic for another day. But to the specific question that's being asked, when I have these antagonisms, what's the best way to get zinc into the crop? So the two methods that I like, particularly for zinc and other micronutrients, I really like starter fertilizers. Putting it in a concentrated band, especially with some nitrogen. Nitrogen tends to stimulate root proliferation, as does phosphorus. So putting that in an NP band in a form that's compatible with that phosphorus solution, putting that in a concentrated band, increasing the concentration, taking advantage of the localized root proliferation, and those roots secrete acidity, so can enhance the availability of zinc. So that's one of the ways I like to get zinc to the crop early in the season. And the other way, obviously, that avoids those soil interactions is foliar applications. Obviously, on small plants, it's a bit more difficult to get it targeted, but a narrow band spray over that crop row might be justified. And obviously that avoids those soil interactions and antagonisms. So that's a great question. That's how I would prefer to approach it. So kind of give your advice, because should fertilizers be applied based on their removal by crops rather than based on soil tests? So I like to consider both pieces of information. I like to consider the soil test. Where am I with my soil test? If I'm at an excessive level, I'm going to be less inclined to apply based on crop removal. But let's say that I'm around that optimum level or near optimum, then I might be more inclined to use a crop removal application to maintain at that optimum level. So it depends on what I'm trying to do. In an excessive soil, I have no problem trying to draw that down and not apply more. So I do want to know what the soil test is. I don't want to go strictly off crop removal alone, because that I might build up an excessive level that's not economically appropriate, or may even create an environmental risk if I get my phosphorus level too high, for example. So I'm going to use both pieces of information in conjunction. So another question, any progress in use of non-destructive soil testing? There are some methods that have been used. There's a particular company out of Canada called Western Ag Innovations, who've been using what they call root simulator probes. It's basically ion exchange resins that they put in the soil, and then you can pull those out and measure the amount of nutrient that's been accumulated on that exchange resin over time. So that's a non-destructive method that has shown pretty good correlation with crop response. So you might look into those probes. Some have attempted to use other imaging techniques. Now the name escapes me. The Varus probe, for example, looking at some of the conductivity tests, although they need to be calibrated as well, and they're less specific to the particular nutrients. So the resin probes are a pretty good technique and have been used pretty successfully in Canada for a number of years. So I'd look into that. Some of the other non-destructive methods are kind of still in their infancy, and obviously crop imaging is being used a great deal these days, although that's looking at the crop response and not really evaluating the soil itself. So again, combinations of these techniques is probably the best way to go. So with that, we're right up against our hour. If there's any questions, now's your time. Remember, if you want to submit your name and CCA number, now's the time to do that, or you can wait. You will all get an email. Everyone registered will get an email when the recording is available. You can watch the recording and get your CCA credits. At that time, there'll be a short quiz at the end we're required to provide for that certification. Thank you all very much for attending. There's some great questions. Lots of things to talk about. This is information that, while not site-specific, does give us some general trends and can point us to particular problem areas that we can look at. So with that, I'm going to say, have a great day. We thank you all for attending and hope you'll join us in our next economics webinar. Thank you.